Okay, we will now give you a demo program which shows you how to turn a 1D diffusion program into a 2D diffusion program. As you can see in the pictures, for 1D you have a temperature along a line, needing only one index to indicate the position of the temperature, and I have a boundary condition in a point at the left and in a point at the right. For 2D, we have two directions, x and y. We need two indices to indicate the position of a variable in the plane, I coordinate and a j coordinate. We need boundary conditions, not just at the left and the right, we still need them, but we need them at the left and the right along a line, not in a point. And we also need boundary conditions at the bottom line and at the top line. As you can see in the third picture to the right, every point has, besides a left and a right neighbor, as in 1D, it also has a bottom neighbor and a top neighbor, so it has 4 neighbors in all. We now turn to the MATLAB program. Let me shortly go through the program. It fixes the number of points, a grid, parameters like delta t, alpha, number of steps, temperatures perhaps to be prescribed at left and right, initiates the arrays to be used, t new and t old, 2 zeros, start of the time loop, computes the time at the new time level, copies t new over t old, time integration step, calculating t new in terms of t old, boundary conditions at the left and at the right, prescribed temperatures in this case, a plotting statement, a pause statement, so that the graphics doesn't start to blink. There's a small interval of 1/10 of a second between new plots, and the end of the time loop. Okay, let's start turning this 1D program into a 2D program. First of all, we also need to indicate how many points we have in the y or j direction. We have a grid in the x direction. We will also need a grid in the y direction. Let's copy paste and turn x into y and I into j where appropriate. And we are almost done with the grid. What we will need for 2D plots is our grid in a 2D array. And these 2D arrays we need for the x coordinates and for the y coordinates. And we will call these plotting arrays, we only need them for plotting, xplot and yplot, and they are now two-dimensional arrays. For the x coordinate and for the y coordinate. Okay, and an end to finish the 2D loop. Okay, we go down. We have an initialization for a 1D array to zeros. We have to turn it into 1 for the 2D array. So the 1 is changed to j max plus 1. And we are now inside the loop. Copying an array stays copying of an array. Here we have a 1D loop. For the time integration, it will have to be turned in a 2D loop. Let's also add the end so we cannot forget it. And this statement for only I direction has to be turned into one for I and j. And the first step is easy. We have to add comma j for all the terms. So that has been turned into a legal 2D statement. And we need something very similar for the j direction. So that means we do some copy paste. I want to tell MATLAB this is one long statement. You do that by inserting 3 dots. And the second part of the statement has to be changed into one for the y direction. So left neighbor becomes lower neighbor, and the right neighbor becomes the upper neighbor. That's the time integration part. Boundary conditions, that's sometimes a bit more difficult. We have boundary conditions at the left point and the right point. That has to be defined along a line. The line varies in the j direction. Only for the interior points. The 1D statement has to be turned into something 2D. We just have to add comma j along the whole line. For each j, we have something similar to 1D. Boundary conditions along the vertical lines. We also need to set boundary conditions along the horizontal lines. That means I have a variation in the y direction. Variation in the I direction, yes. And I'm going to impose, just for easiness, a zero derivative boundary condition. In this case, I have a variation over the I direction. And I want the lowest point to be equal to the first interior point. Ti1 is equal to Ti2. And I want the top point at jmax plus 1 to be equal to the one but top highest point. It's the point at jmax, which is still interior to the domain. These are my boundary conditions. There's a plotting statement which will give an error state message from MATLAB. And the reason is that my t new is now a 2D array and my x is a 1D array. And since I imposed these zero derivative boundary conditions in the vertical direction, my solution will only change in the I direction, in the horizontal direction. So I will just take a part of the t new solution, which varies along the x direction, the dot dot, and has a constant value for the j direction, so it's varying only along a line. And now the program should work. Usually I make 1 or 2 mistakes, but you never know. So if all is well, I now get yeah, it's working. It's a 1D program, 1D problem solved in a 2D program. So you can easily implement more complicated boundary conditions. And for instance, you can decide that you want a more nice plot. What you could do, for instance, is include a contour plot. Now you need these X plot and Y plot. And I only want the interior points. That means j from 2 till I max, j from 2 till j max, and I want that for all points, all variables, sorry. Okay, then I don't want the 1D plot also included, so I will just comment it out. See how far my solution is. A beautiful straight line, that's the validation. It really works. See if it has already stopped. It has. So let's see how the contour plot looks like. There you go. End of the demo.